All right. What's up, everybody? So I no office hours this week. However, I did want to provide something for you as you're preparing for the exam. Um, and I guess a few things of note. One is that there was no homework on chapter 17 on sound, and it sounded like no pun intended, but it seemed like from what I heard this week, that there's some frustration with the speed at which that material is covered. So what I'm going to do is pay particular attention to sound as I'm reviewing this material. The backbone of this review is going to be old exam questions because we're kind of in that final stretch anyway. That's what we should be looking at this point. Um, but I will probably, sidetrack into some discussion of sound and particularly like solving exam problems that have to do with sound. Um, in light of that, questions about how to study are going to be met with various answers. Obviously, old final exams is a good idea. Unlike previous exams, of course, this exam is cumulative and is liable to have questions from your first two exams. So those are important ones to go over as well. And just to remind you that the average of this will be around what the average on the other ones were. So it's going to be you're going to be totally fine. You're going to pass the class if you don't get all 20 questions done. You just want to kind of get the points that are available to you. Excuse me. So as you're going through old exams, if you're not able to attack all of the problems right away, that doesn't necessarily mean that you need to panic. Just keep going through these exams. What you are going to see is particularly with last fall's final. Last fall, the final had quite a few homework problems directly off of the homework. So that would, maybe hint that looking at the homework is worth your time as well. Of course, the way that the homework problems show up, the very complex homework problems are less likely to show up. And even if they did, you wouldn't want to waste 30 or 45 minutes of your 2-hour window working on a very difficult problem. Um, so, that take that with a grain of salt. I do think that your priority here would be to review old exams, to review your exams from the semester. Make sure you can do those 40 problems in case a few of them do show up in the final. And then to look at your homework and proceed from there. I think the first thing I said was old exams, right? So definitely look at old final exams and absolutely prioritize going over the new material because you have not done any exam questions on the new material, which is starting from chapter 13 and moving forward. So it starts with gravity through fluids and then simple harmonic motion, standing waves and sound waves. So in light of that, we'll go ahead and get started with the spring 2021. Sorry, it's like the middle of the night now. A little froggy. Yeah, so starting with spring 2021, let's start there. Um, and I'm going to sort of pick and choose. I'm going to mostly focus. I'm going to focus on the new material. Problem number one looks like it's new material because it's asking about speed of sound, but it's actually just a unit conversion problem. You're just converting from meters per second to miles per hour. Question number two, I do just want to mention because I'm not sure we've necessarily heard the term terminal velocity. That sounds like it's an air resistance question. It is technically an air resistance question. The terminal velocity of something that is falling is just when the air resistance grows large enough that it cancels out the force of gravity. So that's just what's going on there. What's your net force? When the air resistance up is canceling out your gravity down, your net force is of course zero. That is, I believe, the only type of like air resistance question that you're responsible for knowing in this class. And I don't even think you ever have to calculate terminal velocity, but what you would do is you would set mg equal to that force, but there's nothing there that I believe you need to be responsible for. All right, problem number three is an internal forces question. Problem number four is where new material starts. So we'll start with problem number four. Problem number four, we have a nozzle. We're watering flowers and we have 25 holes. It's like a sprinkler, the sprinkler that shoots up a bunch of different jets. So It might sort of sit on the ground like this, and it has 25 holes, and you get all these different streams of water coming out. I'm only drawing 5 of the 25. And each of these is going to have a diameter of 1 millimeter. So each hole here has a 1 millimeter diameter, and it's going to be connected to a hose. And the hose that's going to feed the sprinkler has an inside diameter of 1 centimeter. And they also tell us that it's flowing at 0.5 meters per second through the hose. And we ultimately need to find this velocity at which the water leaves the nozzle. Okay, so a couple things here. First of all, I probably sort of drew this out of order. Probably want the feeding hose on the left side, but it'll be all right. What we have here is we have water flowing from one section of a pipe to another. It's kind of a glorified version of that problem. Of course, the section of pipe that it's flowing into is this weird nozzle thing with all of the holes up here. But ultimately, all this is just volume flow rate problem. And we know the equation, and I do not see it on the formula sheet. That's frustrating. So, oh wait, yes, okay, continuity equation on the formula sheet. All right, so your equation is A1 V1 is equal to A2 V2. It doesn't really matter which piece is section 1 and which piece is section 2. I usually say that the inflow is section 1 and the outflow is section 2. Anyway, so for each of these, we're going to have areas, and the areas take just a tiny little bit of work. We're given 2 diameters, and I know that in both cases, my areas will be pi r squared. So what is my radius? Keep in mind that these are diameters, so I need to divide both of these by 2. Also keep in mind that they are not in meters, so I need to convert them into meters. But let's go ahead and continue work on our continuity equation here. So the area for section 1, which is the hose feeding, is pi r squared, where we have pi, and then our radius is going to be half of 1 centimeter. So that's half of a centimeter, and then, or 0.5 centimeters, converted to meters is 0.005, and that quantity is squared. Then we have times that velocity, which the inflow velocity is given as 0.5. And then on the other side, we are going to have the area for section 2. Now, section 2, we have a diameter of 1 millimeter, which corresponds to a radius of half of a millimeter, which is 0.0005, 1/10 of what I have over here. That'll be our radius. That'll be our pi r squared. Also, however, we have 25 holes poked in the top of the sprinkler up here. So that total area is 25 pi times, I'm going to write it down here because I'm kind of out of room, that 0.0005 squared times V2. This is all in one line. I've just kind of run out of room. Great. And then what can we cancel here? We can cancel a pi. This ratio, when I divide 0.005 squared by 0.00005 squared, that will be 1/10 squared, which is 100th. So I have 0.5 on 100 is equal to 25 times V2. And if you solve there, you'll get that your V2 is 2 meters per second. Cool. All right. What's the overall takeaway? If you have water flowing from one section to another, and especially if you're talking about only just the speed in each, you use A1 V1 equals A2 V2, the continuity equation. If they ask you about pressure in one section versus pressure in another section, that is where you use Bernoulli's equation with the 1/2 rho v squared and compare the pressures between the two sections, all right? And then we have seen problems as well where you have to use both continuity and Bernoulli's because they don't give you enough quantities. But luckily in this problem, we only have to do continuity calculation. Okay, problem number 5 on, again, spring 2021 is a circular hoop undergoing small oscillations about a pivot point on the rim. There's some hints in the way this question is phrased. They also ask us about the period of the oscillations. Whenever you hear oscillations, that should hopefully guide you to chapter 15, where we had simple harmonic motion and physical pendulums. That was the entirety of chapter 15. And of course, a pivot relates back to pendulums. We're talking about a physical pendulum here. All right, so I have a hoop and my pivot is at the top. And I know I need to do a physical pendulum calculation. Good thing we get to practice this once again. 2 pi times the square root of the inertia around the pivot. Oh, how is this written on your formula sheet? Oh, they just call it the inertia I. I guess I suppose I add pivot myself. The way it looks on your formula sheet is the period is 2 pi times the square root of I over mgh. I wrote this as the inertia subscript pivot over mgd. That's fine. I think everyone will still be able to navigate this problem in this form. All right. So how do I proceed with my physical pendulum problems? I need to do 2 calculations. I need to find the inertia at the top, and I need to find the distance from the center of mass to the pivot point on the bottom. Start with the inertia. That's usually the longer part. My inertia here will be the inertia through the center of mass plus the parallel axis contribution to the inertia. The inertia around the center of mass of a hoop is somewhere up there in the formula sheet, and it is mr squared. And then I have plus the parallel axis contribution. I know it's going to be m times h squared. Question is, what is my h? H is the distance that you move from the center of mass to the parallel axis, which is just the same thing in this particular case as the radius. Because our pivot point is on the rim, this is also an r, and then that is squared. And so we have mr squared plus mr squared, which is 2mr squared. That'll be the numerator of the stuff that's under the radical there. On the bottom, we need to calculate our h, which is the distance from the center of mass to the pivot point. Again, and as we've seen quite a few times, this is just equal to the radius of the hoop. If you'd like to see it, you can do the sum of the mi(xi)s over the sum of the mi's. But you should just be able to sort of read off the graph. Okay, here's my center of mass. How far is my pivot from my center of mass? Well, it's just the radius. So that means that the distance between the center of mass and the pivot is the radius. Or we've seen also where it's the length over 2 for a rod. Okay, so I can go ahead and plug that in. I can plug both of these into my period equation, and I'll have that the period is 2 pi times the square root of, my numerator is 2mr squared. My denominator is m, it's the same m, big M, times g times big R. And I can simplify a little bit. My 2 pi times the square root of my m's will cancel, and one of my r's cancel. So I have 2r over g. And looking at my givens of the problem, I was given the mass. The mass doesn't actually factor in because it's canceled out. And I was given the radius. That's actually the only thing I need. And I can plug that in up top. And if you do that, then you'll get that the period is 1.4 seconds. These are the types of physical pendulums that you'll be most responsible for. Also, this simplification, this is similar to the one that you had on the homework or on the quiz this week, if you did happen to get that problem. Where you just have one single object, a lot of stuff cancels, and you end up with a simplified expression for your period. And so it can make the problem seem a little more daunting on the front end because all you really need to be given to answer this is just the radius. Uh, but yeah, ultimately there is a little bit of algebra to do. On the homework, you had a more complex physical pendulum and less stuff canceled out in both homework problems. But this is more in line with the type of exam problem physical pendulums that you should expect. All right, problem number 6. Problem number 6 says we have a mass on a spring undergoing simple harmonic motion. Thank you for being explicit about which section I'm in. That's helpful. The amplitude of the oscillations is 1 centimeter. Just write that down. Paying attention to the fact that centimeters need to go to meters before I can do anything with it. Maximum velocity is 0.1 meters per second. Vmax is 0.1 meters per second. And I want to find the maximum acceleration. All right, so quick sidestep note here. If looking at the formula sheet from last semester, you'll notice that for simple harmonic motion, we are given exactly 2 equations. Omega is 2 pi f, or it's 2 pi over the period. And also the general form of the position as the amplitude times cosine omega t. We are not given this list of very helpful simple harmonic motion equations. So if you have the time and the patience to try and memorize these equations, this is going to make your life much more simple going forward, or less frustrating if you happen to come across a simple harmonic motion problem. And this would just be your first thing to write down on your notes page. There are going to be a few equations that are not on the formula sheet that I'm going to mention that we have made use of throughout the semester. All right, so in simple harmonic motion, we know that we define, well, your amplitude is going to be your x max. So this is just a definition. And in light of this, we could say that V max is equal to the amplitude times omega, and A max is equal to the amplitude times omega squared. If you get to the exam, you forget these equations, you do have the generalized position function, x max cosine omega t. And if you'd like to derive this relationship and this relationship, you just need to take 1 and 2 derivatives respectively. And whatever ends up outside of your cosine will be x max omega squared. Okay. For omega, as I mentioned, we have 2 pi f, we have 2 pi over t. The other omega that we do not have, I don't believe anywhere on the formula sheet, is that omega is the square root of k over m. And that is a very useful definition. As a reminder, this is the spring constant and the mass. So this is for an oscillator with a spring. But that is a very useful equation that is unfortunately not on the formula sheet. If you needed to derive this, you could, of course, use the mechanical energy. I think I showed that a few weeks ago. You could use the mechanical energy definitions and derive that in a pinch on the exam. On that note, mechanical energy is also not listed here, but we have done problems with mechanical energy. So remember, your mechanical energy is 1/2 k times the amplitude squared, or x max squared. And it's also 1/2 m times v max squared. And again, the reasoning is that this is your maximum potential and this is your maximum kinetic. Okay. All that is to say that with this problem, this is actually a relatively straightforward problem, just 2 little equations that we need to calculate. I know I'm given V max and the amplitude. I know I need A max. I know that in order to use this equation here, I need the amplitude and I need omega. Where am I going to find omega? Well, that's going to come from your V max definition. So this is equal to A omega. I have A right here, so I can plug it in and I can find omega. And that'll give me that omega is V max over A. And then in order to find A max, I just need to replace omega with this expression, V max over A, quantity squared. And what will I end up with? V max squared over A. And then you can plug in your V max and your A. We did quite a few problems like this on the homework, and also this was a quiz problem this week. So hopefully you've practiced sort of using two simple harmonic motion equations. Compellingly, though, it's only simple to use those two equations if you happen to know them. So I don't uh, suggest memorizing a whole lot in this class, and I'm not even sure it's worth memorizing the equations themselves. But I think you should make sure that you either know these equations or you know how to get them from the x of t function. If you don't know either, then you would simply not be able to do this problem. All right. Problem number 7 has to do with a graph, kind of pixelated graph there. And not the greatest diagram, but we have a wave that is moving in the x direction. So this is actually a chapter 16 wave, a wave on a string. And at time t equals 0, it has its maximum at y equals 0, and then, excuse me, it's oscillating like this. And sometime later, which they call t1, it's moved just a little bit so that its maximum is right here. Now the diagram looks a little bit different on the exam, but I'm just sort of emphasizing that I'm tracking the maximum from right here on the first graph, and I'm seeing that it's over here on the second graph. Why is that important? Well, I have these vertical dashed lines that correspond, let me use yellow. All right, so these are going to be the vertical dashed lines on the graph. And I have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And on the graph, they say that this right here is 1 meter. This is why I want to track the maximum, because this is divided up into fifths by those vertical lines. This 1 meter is divided up into fifths. And since my maximum has moved only one vertical line over from the initial picture, that means that it's traveled over 1/5 of my 1 meter. So that you could think of as a delta x. It would be delta x is 1/5 of a meter, or 0.2. The next thing is that they tell us that t, they call it t. They say t is 0 seconds and t1 is 1 millisecond. So it's moved 1 meter in a time of 1 millisecond, which is 0.001 seconds. So I have a delta x, I have a time. They ultimately don't ask me for my velocity. That's probably right where your head goes, right? You think, all right, delta x equals velocity times time, I can find the velocity. But they don't ask for the velocity, they ask for the frequency. So let's investigate how to attack this. First thing is, as I just mentioned, yeah, you delta x, oops, what happened there? That was seconds, okay. Your delta x does equal velocity times time. And yeah, so we know we want to use this equation, we know delta x, we know time. Ultimately, though, we do not want velocity, we want frequency. And you may look at your formula sheet and see if you have a definition that relates the velocity to the frequency, and you do. It's under wave speed, under traveling waves at the top of part 3. Your v is omega over k. Oh, yeah, no. V is omega over k, lambda over t, or lambda f. So that is the equation that we want. V is equal to lambda f. And looking at these two equations, I could perform a substitution and see that I have delta x is equal to lambda f times t. And I'm doing all right here. I know delta x and I know the time right here. The only thing that I don't have here is lambda, the wavelength. And so I ultimately need to yeah, okay, so my problems, my diagrams are x distance on the horizontal axis, Sorry, it's like 5 in the morning. The x distance is on the horizontal axis, and I know how to read a wavelength. So remember, so long as my horizontal variable is x, I can read wavelength. If my horizontal variable is time, then I read period off of a graph. All right. What is one wavelength then from positive maximum to positive maximum? The one exception was that dkdt graph where it was a cosine squared, but that was an exception. For the most part, if I'm just given like a y, this is just going to be one single cosine wave, and this is going to correspond to a wavelength. And I just need to read off on the graph and count off the little vertical lines. As I mentioned, there are 5 vertical lines corresponding to 1 meter. And if you count up the vertical lines up here, you end up getting 8 vertical lines. So 5 lines is 1 meter. That means that 8 lines is 5 plus 3/5. 5 plus 3/5. That's how I get a wavelength of 1.6. You could also set up a ratio if that isn't immediately apparent to you. But the point is that I have faith that you can read the graph so long as you know that you're supposed to. I think you've probably practiced reading that graph before. All right, and then there we have it. That is our lambda. We have our delta x, we have our time. We plug those 3 in and we can solve for the frequency, and we get a frequency of 125. Units don't matter here because all of the answers have the same units, but just to point out that if you didn't know which frequency you were looking for, you could look at the units on the answer choices and see that it is hertz and know that you are finding the frequency f, not the frequency omega, which is in radians per second. Cool. All right. So that is the new stuff for which we have done homework. We now have 3 questions um, on this exam, which are new stuff for which we did not have any homework this semester. And this is going to be interfering waves, standing waves, harmonics, and sound waves. So the first one is a harmonic standing wave. And for this problem, I will just mention that we do have stuff in the formula sheet where it says resonance, and you have 2 equations, open or closed on both ends or closed on one end. You can use those equations. However, you need to know the names of the harmonics. Now, I guess I should take a step back because we haven't even really covered this. I guess you covered it a little bit in lecture. So what is in harmonic or a standing wave? The most common example is, I guess, a jump rope. You probably don't have enough tension in a jump rope that is technically a harmonic. You'd probably want a tighter tension. So usually it's a taut string that you like pluck. Oh, a guitar is an example, right? So a guitar string is fixed at both ends. And when a guitar string, this is sort of the natural state of the guitar string. When you pluck it, it vibrates back and forth between these positive and negative maxima, but it has the same fixed ends at one side, and then it has the same maximas location. Now, you can also do something which is called a pinch harmonic on a guitar. I might be kind of losing the plot here, but a pinch harmonic is where you lightly tap in the middle of the string, and what happens is you get a much higher frequency out of that string. And what's happening there is by touching your finger in the middle of the string, you're creating another node. So you're creating another fixed point on the string, and you're getting a vibrational pattern that looks like this. So what has happened here, again, is we have produced a different frequency, which is a much higher frequency or a greater frequency. And we've done that by touching it in this, touching the string in the center. And we've created another resonant harmonic wave, which is a standing wave here. But unlike the picture up here where we just had half of a wavelength, now we have one entire wavelength on the string. And if you had enough hands and enough fingers, you could touch the guitar in two places in the middle, and you could produce a uh, you would then have, obviously the two places where the string is screwed into the guitar, and then the two places where you stick your fingers, maybe losing the plot in this example. And you create a standing wave in harmonic that looks like this. So it's vibrating back and forth. Anyway, you could also do this experiment if you have like a piece of rope. A cable isn't great. I don't have any rope or anything around here. But if you have a piece of rope nearby, um, you can pull it really tight. And what you can do is you can shake it. And at first, you'll just get the single vibration up and down. And then if you increase the frequency that you're shaking, you'll be able to produce a standing pattern that looks like the second harmonic and then the third harmonic. All right, so I've been using names here, and each of these names has a corresponding um, uh, letter. So we have the fundamental harmonic, which is n equals 1. And then we have the second harmonic is n equals 2, and the third, which is n equals 3. And this is for when we are closed at both ends. We could also have a wave which is open at both ends. And you'll also notice that there's an equation there that says closed at one end. So how would we have a string that's open at both ends? Well, the string sort of falls apart there. And what you really have to fall back to is sound waves with things like instruments. So um, a uh, oh, I don't want to upset uh, band people. I'm not sure exactly which one, like a woodwind, which one's like open. I think a woodwind is open. A flute's open on one end. Yeah, I think a flute is a good one. 'Cause I'm pretty sure there's like a little hole that you produce the sound. That's how you put the sound into the flute barrel. Um, but it's open on one end and it's closed on the other. So that would be an example where you'd use the closed on one end equation. There you'll notice your end goes 1, 3, 5. So the fundamental harmonic for closed on one end is 1. The second harmonic is 3. The third harmonic is 5. Now, I'm also going to show you here how to just answer these problems every single time without those equations. And you could answer this problem that is problem number 8 here. You could answer this using the equation for open or close at both ends. Plug in n equals 3 because we have three like humps in that wave. And yeah, and then plug in your V. The other thing that you can do is, and I'm going to redraw the picture here. Okay, we're going to need that. Just a second. The other thing that you can do is, I know that I'm given mass, length, tension. Tension when I'm dealing with waves should make me think of V is equal to the square root of the tension over the mass per unit length. That's the only place that it shows up. If I want to find a frequency, and I've got the tension of the mass per unit length and stuff, and I want to find the frequency, then I'm going to use my other definition for velocity, or for wave speed, which I've already used a few slides ago, which is lambda f. V equals lambda f. That one comes up a whole lot. All right, so ultimately, you don't need to know the n equals 1, 3, 5, whatever. You don't need to know any of that so long as you have this relationship in mind. And so long as you can read the wavelength off of this picture. So this string has a length of L. It's given, mine says 0.9 meters. I think everyone has the same version. Anyway, what is one wavelength on this picture? However, one wavelength is just going to be from here up, back down, and then back to the middle. That is one wavelength. How much of the length, here I could probably label that. This is the wavelength. How much of the length L does that correspond to? Well, that's 2 out of the 3 humps that we see in the picture. So that's 2/3 of the length L. And that's it. That's why there's like an n over 2, because when I reciprocate, my n is 3. and the 2 ends up on the bottom. That's why the L is on the bottom. But if you just want to use the picture, you can sort of generate this relationship yourself. And then from here, you're good to solve. So yeah, so we want to find the frequency. Plugging this in and solving for the frequency, I get the frequency is 3 on 2L times the square root of tau over mu. Notice that general equation has NV over 2L. My N is 3, my V is square root of tau over mu, and then there's my 2L. So I've sort of regenerated that equation. Maybe this will help somebody to see where it comes from. And in the problem, I'm given my tension explicitly in newtons, so I can plug that in on the top. I do not have mu, and I have mentioned this and alluded to this a few times, but remember that mu is mass per unit length. And if you're not given mass per unit length explicitly, as is the case here, I need to generate my own mass per unit length. So it's a mass of 5 grams spread over 0.9 meters. That 5 grams is 0.005 kilograms over 0.9 meters, and then whatever that is would be your mu. And we go ahead and plug that in for mu, plug in your 300 newtons for the tension, and plug in a length of 0.9, and you'll get out a frequency of 390 hertz. I guess I should mention that there are multiple versions of each of these problems. I have one version and other people might be getting a different one. So if the numbers look different here, if the answers look different, there's a decent chance that we have different versions. And I apologize for not making that clear sooner. Okay. Great. I think that that covers standing waves. That checks off at least 2 lines on the answer sheet, so you know what's going on with those 2 lines and when to use them. As I mentioned, also if you have a pipe, and you're producing a sound like an organ is a standing resonant wave in a pipe. Anyway, those are just some applications. All right, we're going to move into problem number 9, and this is going to introduce another topic with sound waves. And this one is also not covered on the formula sheet, which is nice. Yeah, not anywhere in the formula sheet. I guess they give us superposition of waves, and then they give us this completely useless equation that has sine of alpha and beta as 2 cosine. I don't know why it looks like an identity. I don't even know what alpha and beta are supposed to be there. All right, and they don't even use it like in the solutions to anything. Whatever. Anyway, all right, we have 2 speakers producing a sound of a given frequency. Here are my keywords here. They're pointing directly at one another. There's a point P on a line between them. My keyword is that there is complete constructive interference. Constructive interference. Interference, I guess, is probably the biggest key there. We'll talk about constructive versus destructive. But at the very least, if you see interference, hopefully that will set off a light bulb and refer you back to this problem. Too bad I cannot spell interference. Great. All right. Yes. So trying to think of some examples of interference that you will have encountered in the wild. Definitely if you've ever been to like a show, and probably also happens, it's probably less so in like a bar or club, because usually those speakers are so loud that like you would never hear the destructive interference. But interference is, I guess one application is like the construction of amphitheaters, like even back in antiquity, like Roman and Greek times. They didn't have any microphones, but what they did is they built these amphitheaters, which are like, so here's your stage, right? And then you have these like cascading rings of audience out like this, and that's sort of your, your amphitheater. And at each cascading ring, you had a certain width and a certain height that they went up. And so you'd have sort of this escalating, cascading seating area. But also the widths were very particularly chosen. The like widths of each row were chosen to produce constructive interference. What this meant, this constructive interference, is that an actor could sit on stage or standing on stage could whisper, and that might be a little bit of an exaggeration, but the idea is that you can speak softly on stage, and because of the shape of this auditorium, you produce constructive interference. What is constructing? Well, you would have a sound wave that comes from the speaker's voice, and then you'd also have like an echo that's bouncing off of other parts of the amphitheater. And so all of these different echoes are all arriving in sync and creating constructive interference, which allows you to hear something which you shouldn't normally be able to hear if you were just standing in a field at this distance from this person. You can now hear that thing because these sound waves have built each other up and created what's called constructive interference. Now, the flip side can also happen. And if you've ever been to, definitely have been to shows where the sound was not set up properly. And as a result of the sound not being set up properly, the waves arrive out of sync. And since they're out of sync, they actually destroy each other, and that's called destructive interference. All right, so I guess that is an introduction to interference. What are the actual problems that we're going to have to do? Um, Ultimately, the concept of interference all comes down to the difference in the distance that waves have to travel. So if I have two speakers, just to start, let's say that I have two speakers. This is like kind of a bird's eye view. Let me try to make these a little more. Yeah, okay. So my sound's coming out of this side, and sound's coming out over here. Um, so constructive interference happens, first of all, if the sound has to travel the same distance. So if I'm standing like right between the speakers right here, the sound from each speaker is traveling the same distance, and that means that the two waves are going to arrive in sync, and they will build each other up, and I'll have constructive interference. If I happen to move to a place where one is at, say, a positive maximum and the other one is at a negative maximum, it could just be a little bit of a distance over here to this point. If this one is at a positive max, called positive amplitude, and this one is at a negative maximum or a negative amplitude, they are out of sync and they'll cancel each other out. So how do we determine this? Well, notice that I've talked about where, like if it's at an amplitude, if it's at a positive or negative amplitude, that is always a question of the wavelength and where within your wavelength you are. All right, this is sort of my motivation. So what I actually need to know is not necessarily where each one is in the wavelength, but I need to know the difference between them. If the difference between them is half of a wavelength, as it would be at my blue dot, where delta L is half of a wavelength, then that's going to be destructive interference, because one is up while the other is down, and they destroy each other. If, like I have at the red, the delta L is 0 for one, then obviously if the delta L is 0, we have constructive interference. Now, the other thing that I haven't mentioned is that you could keep going and arrive at another point where you are again in sync and you have a positive amplitude and a positive amplitude. So this pattern, in other words, repeats. If your delta L is a multiple of lambda over 2, so if it's lambda over 2, or if it's 3 lambda over 2, or 5 lambda over 2, then you have destructive interference. If delta L is a multiple of just lambda, then you have constructive. How could I generalize this? Well, you could say that for each of these, this is a definition, and then for each of them, you could add an n lambda. But let's take a look at how to apply it. So in this exam problem number 9, which I'm building up to, we're told that we have these two speakers pointing directly at each other. So this speaker is pointing at this. Oh, no, I wanted it pointing at each other. Speaker. Cool. And they're going to produce the same sound with the same frequency. That's good. You have to have that to even do a consideration of interference. There's a point P on the line between the speakers where there is complete constructive interference. We want to know what the shortest distance is that we can move to get complete destructive. All right, so we're at a point P. At P, we have constructive interference. Without really messing around, we could just say that that point P is directly in the middle where delta L is 0. So these speakers are a distance. Let's not use L for the distance, and we're also not going to use D because D is given the problem. They are some distance. I think we could just use X. Cool. They're distance X apart. It's not ultimately going to matter. It's going to cancel out. If I pick my point to be at the center, halfway between them, then this would be X over 2. And this would be X over 2. And my delta L, when I'm at constructive interference, would just be X over 2 minus X over 2, which is just 0. Now I'm going to move my point a distance D away. And I'm going to get destructive interference. So I want to get to a point D where delta L is destructive. Destructive means that delta L would be lambda over 2, or 3 lambda over 2, or 5 lambda over 2, or so on. And I can go ahead and calculate delta L just as I've done before. Now up here we had X over 2 minus X over 2. Now we have to incorporate this D. So for the left speaker is now X over 2 plus D. We've added in D over here. So we'd have X over 2 plus D minus the second speaker's distance, which was X over 2, and then we've subtracted D from it to get to our new point. So this is X over 2 minus D. And cool, there we have our delta L, just the two different lengths, the two different distances from speaker to point. And we can go ahead and simplify here. X over 2 is going to cancel out of both. We have D minus negative D, which is going to give us 2D. And then we have lambda over 2 on the other side. Ultimately, we are asked for the distance that we need to move it, which is lambda over 4. And my lambda is not given, so you might think you're in a little bit of trouble. However, I do have a frequency and I have a velocity both given in numbers. And again, old trusty reliable, you notice this keeps coming up, v equals lambda f. Plug in your velocity, 340, plug in your frequency, mine happens to be 680. So 340 and 680 means that this has to be just a half, right? And so you plug in a half for lambda, and that's how you get a D of 0.125, 1/8, right? That's, yeah, a half divided by 4. All right. So this is the concept of interference, constructive, destructive interference. This is a little bit of hand wavy, but you don't really have anything on the formula sheet. So I suppose you do need to know how to just sort of construct this from the ground up. Just to give you a generalized list of equation, you'll see it in your what's it called, in the solutions to this problem. But just to reiterate here, we have constructive interference when delta L is equal to n lambda, such that n is equal to 0, 1, 2, whoops, that's supposed to be a comma, 0, 1, 2, so on. And we have destructive when delta L is equal to n plus a half times lambda, where again, n is an integer, 0, 1, 2, and so on. You rarely have to go to higher ends. Most of these problems can be solved with like n equals 0, and you're just going from where this is 0 to where this is a half lambda, just like we did in that last problem. So yeah, I think you're pretty safe there. I suppose they could also give you like a predetermined delta L and ask you to figure out if it's constructive or destructive. This type of problem, though, is much, much more common when it comes to old exams. The one that we just did. All right, problem number 10 is the Doppler effect problem. And a quick note about Doppler effect. I'm going to, I guess, explain it a little bit, and then I'm going to do the problem. But before I even do that, I do want to um, just mention that there are as many ways to do the Doppler effect as there are like people who teach this class, and every single method of doing it has its drawbacks and not. So I'm just going to teach you, my method. I'm going to acknowledge the drawbacks, or just like one kind of big caveat. But this is just 10 years of teaching this, and this seems to be the way that is most digestible for people. What is the Doppler effect? The Doppler effect is what happens when a car is coming at you and it sounds like it's a higher pitch of the engine, and then it goes past you and the pitch drops and it drives away at a lower pitch. So it's like me, right? That me and the approach, you're being Doppler shifted up. You're getting a higher frequency than is actually being emitted by the car. And then that mirror drops down as it goes past you, and that's your frequency dropping. Why is that happening? Well, as the car is approaching you, it's emitting a sound wave, but then it's sort of catching up to its sound wave, and that causes them to be scrunched together. So your ear ends up hearing a little bit of a higher frequency because as the car was approaching, the sounds it emitted got scrunched up, and the frequency that you actually hear in your ear is higher than the frequency that the car was emitting when it was approaching. As it's leaving, it's just the opposite effect. The car emits sound waves but travels away, and that causes them to become more spaced out. And so what your ear hears is it receives more spaced out wave fronts, and so your ear perceives a lower frequency than what is actually being emitted by the car. What is the true frequency? It's somewhere in between the two ones that you hear, but that would be the frequency of the source, all right? So the equation that you're given on the formula sheet, I suppose I will start there so you could at least use your formula sheet equation, is that the frequency, yeah, okay, frequency that is observed, that's you standing on the side listening to the car, the frequency that you observe is equal to the frequency of the source, this is the frequency emitted by the car, times the speed of sound plus or minus the speed of the observer. Uh, this is actually velocity of the observer over the speed of sound again, plus or minus the velocity of the source. Okay, so here's the world of trouble with this equation. It's those plus and minus signs. They don't correspond. They don't really make a ton of sense. The top is supposed to be a plus when the observer is getting closer. The bottom is supposed to be a minus when the source is getting closer. That is the general rule and how you can approach this. I have a little bit of a way that I like to approach these every time, which is to set my observer, my observer always on the left and my source always on the right. And here's why I do that. All I need to do is figure out the relative directions between the observer and the source. And once I do this, then I can just use my corresponding directions for the positive and negative x-axis. So in this problem here, problem number 10, my version says two vehicles are going away from each other. If they're going away from each other, these are their velocities. I don't really care which one is on which side or whatever. And I can just proceed from there as long as I know which one is the source and I know the magnitude of its velocity, and then I'm done. If they tell me that they're coming toward each other and one is on the left, the other one's on the right, if they're coming toward each other, I just draw the vectors so that they're pointing toward each other. And then I know the signs on my velocities that I need to plug in to this equation. So for this problem, two vehicles going away from each other. A siren on the vehicle at the right, moving to the right. I don't care that it's moving to the right. I just care that it is the source because the siren is on that car. So they tell me that the siren on that car, that the vehicle itself is moving 60 miles per hour, and that's my source. So my source is moving to the right. So this is 60 miles per hour, which is going to have to be converted to meters per second. A person in a car is moving to the left. I don't care that it's moving to the left. This car is my observer, so I just need to know the magnitude of its speed. Magnitude of its speed is 30 miles per hour. I already know because they're driving apart that this observer is moving to the left, and that will be a negative direction because we're using our positive and negative sign conventions from chapter 2. All right, and then they give us the frequency. They give us, they tell us that the siren has this given frequency, so that's going to be your source frequency is 10,000 hertz. And then they give us the speed to use as the speed of sound. That will be the V of your source. And cool. So how would 30, let's convert these first of all. So 60 is going to be 60 miles per hour is 26.67, whatever, meters per second. And this guy will be negative 13.3 meters per second. I wish they didn't give it in miles per hour. Just feel like that just makes it even more complicated. All right, how are we going to calculate here? Ultimately, we just want the frequency that is observed. So your frequency observed is equal to the frequency of the source, which is 10,000 times velocity of sound, or speed of sound is what it really is 340. And then the velocity of the observer is negative 13.3 over speed of sound again, 340. That'll be the same on top and bottom every time. And then the velocity of the source is positive 60. I'm sorry, positive 26.7. And there you go. We handled our sign conventions using this setup. Again, we did not pay attention to right and left. It so happens to be that the right and left in the problem corresponds to my diagram. That won't always be the case, and sometimes they'll flip them just to be complicated. But we can plug all this in, and for these numbers, you get 8909 hertz. That's supposed to be a Z. That was very close to being a Z. All right, and so we've emitted 10,000 hertz. We've received about 9,000 hertz. So that means that there is a drop. Why would there be a drop? Well, because my two things are moving away from each other. If you're moving away, that's not the car approaching you, but the car driving away. You have a lower frequency observed. So that's what this mimics. Great. So we have these two both moving. This is one Doppler effect problem. I think we're done actually with this exam as far as new stuff goes. I think, yeah, the rest of this looks to be review. Yeah, cool. So let me pull up the other one and see if we have another, hopefully we have another Doppler effect problem. Oh yeah, we do have quite a bit of new stuff. Yeah, oh, what, 13 questions on old and new. Okay, so what I'm trying to determine here is if I should do more of these problems or talk a little bit more about what's on the formula sheet. I suppose I want to cover, okay, there's 4 equations that I want to cover on the formula sheet, starting with intensity. The intensity equation says I is equal to power over area. This is power, and this is cross-sectional area. you know that it's an A, but just mentioning that it's cross-sectional. What is intensity? Intensity is how loud a sound is. It's just loudness. The power is how loud your speaker is set up, or your headphones or whatever. The intensity, if you're some distance away, will depend on that distance. So we want to take the power, the volume that you set on your volume knob, and we want to divide it by the cross-sectional area. Cross-sectional area of what? Well, typically you have a speaker that is, you know, blasting music out in all different directions. And so that cross-sectional area would be the area of a sphere, theoretically. And so that would be a 4/3 pi r squared, pi r cubed. Nope, that's a volume. What? And come on. 4 pi r squared. So that's your cross-sectional area. Now, if you have a speaker that's sitting on the ground, which is much more common, then you'd only actually have half of a sphere. You'd like cut this thing off. And so your cross-sectional area is actually 4 pi r squared over 2. I've seen problems like that. Anyway, that's what that intensity equation is about. Next to the intensity equation, you have a speed of sound. This is just kind of a one-off equation that you'll just randomly use, but I just want to explain what the variables are here. B over rho. Rho is what we expect it to be. This is the density of the material that the sound is traveling through. So for instance, if I needed the speed of sound in air, we know the density of air is 1.29 kilograms per meter cubed, right, from a few chapters ago. However, if we have a sound wave that is actually traveling through a material, that material will have some other density. And it will also have something that's called the bulk modulus. Bulk modulus ties into deformation, which I only just realized as I was preparing to do this video. We did not cover this semester. But anyway, it is just a constant that relates to, you know, how tightly packed the material is. You could think of it as sort of a relationship to density. Not quite, of course. It needs to be more so related to time. But regardless, at least you know what these are. If you come across a problem where they tell you this is the bulk modulus, then you'll know to plug it in there. And this will let you find the speed of sound again in a material. Typically, the speed of sound in air is, I think on the last problem we just did was 340 meters per second, or it'll be 343 or 330 meters per second, something like that. We did the Doppler shift. Next to the Doppler shift is an equation for something called a beat. What is a beat? A beat is when you have two waves that have slightly different frequencies. If you've ever tuned a stringed instrument, if you ever tuned an instrument at all, actually probably, but I know when I have to tune my guitar, if it's out of tune, I can hold the fifth fret of the top string, and then I can pluck the top string or the low string and the second lowest. And by holding the fifth fret and the lowest string, I should be creating the same frequency in both. And if I'm creating the same frequency, then they just sort of resonate at the same frequency and it just sounds like one note. If they're slightly off, if my guitar is out of tune, I hear like a little wave vibration. And the farther out of tune they are, the harsher that vibration. This is how some beats are produced in like EDM music, is actually by producing two sounds with two different frequencies that are a certain distance apart. And so the difference between those frequencies also gives you the frequency of that wave, right? So if I have, you know, one string is at 340 hertz, another string is at 339 hertz. Wait, I should just do 440. One's at 440, one's at 439. They're very close together, which means that the wave, the whoa, is very subtle. You see like a whoa, whoa, whoa. And the frequency of the wah wah wahs, that is determined by the difference between the frequencies. So if I have 340 and 339, why do I keep doing three? Anyway, the point is if they're one off, the difference between those is 1 hertz, which is 1 wave per second. And that's why you have only, you know, just a very subtle wah wah wah. Okay, so that's your beat equation. It'll be very clear what they're asking you to calculate. If they'll just ask you for the frequency of the beat, but just know that you have to find usually two different frequencies. You could also do it with a Doppler shift, where you have a Doppler shifted wave, or you have the same wave that is shifted one way with Doppler in one situation, shifted another way in a different situation. It'll ask you what the beat is from the two different shifts. Okay, and then the last equation that I do want to talk about is the very last one. Says sound level. It looks like this. Beta is equal to parentheses 10 dB times log 10 of I over I naught. All right, all this stuff is new. This is what is called the decibel level of the intensity. This is the more colloquial version that you're probably used to hearing, where whenever sound is spoken of out in the news or whatever, they're usually talking in decibels. And you could look up a decibel chart if you want to. You can go ahead and Google it. That there's one that has like like a baby crying versus like an airplane, and there's all these different levels. And the important thing here is that a decibel is actually on a log scale. So like if you go up by, if you increase by 1, that's an order of magnitude. You go up by, yeah, each one corresponds to an order of magnitude. That's how log scale works. Anyway, point is that you don't need to necessarily know how to read it. You just need to know that, first of all, this is a constant. This is just 10 decibels out in front. And what you plug in here is you plug in uh, your sound level in terms of some initial, and this is an intensity, and this is the intensity that is the power over area that we had a few pages ago. Anyway, long story short here is that this is just a unit conversion problem or unit conversion equation to get our intensity from watts per square meter that comes from here into something a little more commonly used, which is the decibel rating. All right, I digress. All right, so I am going to do, I don't even know how long I've been going. I feel like I've been going for quite a while, but it is the middle of the night, so anyway, it's a long story. I was trying to go back to sleep, and then a cockroach landed on my arm, and I said, well, I'm awake, so I guess I might as well record this video because I'm not going back to sleep after that happened. All right, so I'm going to switch over to fall 2020 final exam, and I'm going to look at some of the new material questions. A lot of these questions actually come from homework problems that we already did this semester. So I'll just sort of point those to you and also use this as motivation for like, maybe it is worth it to review your homework. All of those homework videos are up. So you could watch them. You could watch them in double time or whatever, or just sort of click through to the problems that you don't feel as confident with, all right, so we have a planet, 10 times the mass, question number 1 here. Planet with 10 times the mass of the sun of the Earth and 3 times the radius. What is the gravitational attraction on the planet's surface as a factor of the Earth's acceleration? What's my acceleration due to gravity equation? It's gm over r squared. What would happen to this if I were to multiply the mass by 10 and the radius by 3? I'd get a new acceleration due to gravity on this new planet. That'll be g times 10m over 3r squared. Pull out my numbers. I have 10 over 3 squared, which is 9, times gm over r squared. But this right here is the expression for the acceleration on Earth that we just described. And so my ratio is just whatever the numbers are out in front. All right. Problem number 2 is 4 particles line the corners of a rectangle. Rectangles have different side lengths. We want to know the gravitational potential energy of the system. For 4 particles on a rectangular arrangement like this, where we have side lengths of r and 2r. We need to find a gravitational potential energy. All right. So I know that first of all, gravitational potential energy, the general equation is that it's negative g big M little m, or m1 m2. These are all going to be the same m anyway, so it's going to be m squared on top. over the distance. I'm going to use little r here to differentiate from that big R in the picture. Excuse me. So here's the rule for potential energy, just to drill it into your head. There's one potential energy term for each pair of particles. So if I have 4 particles, I have 6 pairs. And I can go ahead and label all these particles, and I could go through and do the subscripts, call them particle 1, 2, 3, and 4, label the scripts that label each of the pairs. So you'd have like potential energy between 1 and 2, potential plus potential energy between 1 and 3, plus potential energy between 1 and 4, plus potential energy between 2 and 3, plus potential energy between 2 and 4, plus potential energy between 3 and 4, and write out all 6 of those pairs. And you may want to do that. Maybe you would check your work after you finish your exam and you still have some time. Maybe you go back and do that. However, I am going to expedite the process just a little bit by looking at some symmetry in the problem, which is a little risky. I'm playing with fire just a little bit, but whatever. So where should we start? Let's start with the closest. So here's one pair that is a distance big R away, and here's another pair that is also a distance big R away. So I have, if I'm doing my total potential energy, I have 2 pairs which have gm squared, obviously, over that distance, which is just 1 big R. All right, so there's 2 of my 6 pairs taken care of. Next up, I have this pair and this pair, where the distance is 2R, and it's the same for both. So again, there's 2, so I do 2 times gm squared over 2R. And then I have one other type of pair, which is on the diagonal, right here and right here. What is that diagonal distance? Well, let's start here. I have 2 of them, and they're both going to have gm squared on top. What is that diagonal distance? Let's do that now. I have an r by 2r rectangle. The diagonal of an r by 2r rectangle will be r squared plus 2r squared square rooted. So that gives you, since the 2 is also squared, you end up with 5, right? 5r squared, and take the square root. So it ends up being down here, r root 5. Okay, and then yeah, you pull out the 2 here, pull out the square root of 5 there, combine everything together, and ultimately you'll end up with 2 plus, well, 2 over 2 cancels, so 2 plus 1 plus 2 on the square root of 5, and if you add those all together, you'll get 3.9 times gm squared over r. All right, that's a good review of how to do potential energy. Let's see. Question number 3. Astronomers observe a small planet in a circular orbit, and yeah, we're just asked to find the period. We're given a radius and a period, and we're asked to find the mass of the star. Cool. So for this, you have law of periods on the formula sheet. Again, 2 pi squared, 4 pi squared r cubed over gm. You just plug in everything. The only thing you don't have is the mass, so you just solve it for the mass. And then, yeah, just make sure that you convert from years to seconds. That continues to be one of the biggest curses that has afflicted some people this semester. It's not converting to base units before doing calculations. Just always convert to base units, always. Question number 4, spring of spring constant given is between a rigid beam and the output piston of a hydraulic lever. As soon as I see that, alarm bells start going off. I know I'm doing F left over area left equals F right over area right. All right, that's as soon as I see hydraulic. That's a hydraulic equation. My force over area equals my force over area because the pressures are the same. All right, from there I can then go back and say, all right, I have a spring on one side. and they say it is on the output piston. They say an empty container with negligible mass is on the input. The input piston has an area of A1. That's where my container with negligible mass is. The output, which is the spring side, has an area of 23. Okay, so let's go ahead and plug all this in. I'm gonna put sand in. They want to. It's just like the homework problem. I'm gonna put sand in. That's gonna be my mg. That's gonna be my input piston. So we'll do that on the left. Your input is mg. The area over there is just called a sub I. Your output is gonna be kx, and that area is called 23 a sub I. And what else? Okay, yeah, we're going to compress the spring a certain distance. So I have the spring constant, 21,000. That's newtons per meter. That's base units. Plug that in for K. I also have that the compression distance of the spring is 5.3 centimeters. So that's 0.053 meters. I can plug that in for X. I can cancel out these A sub I's. G is 9.8, and I can solve for the mass. In light of all of that, you'll get a mass of 4.9 kilograms. All right, just like the homework problem. But again, motivation also to look back over your homework if you haven't. Problem number 5 is also identical to homework problem. You're given the density of a ball relative to water. The ball is pulled beneath the surface. You let it go. The ball goes up, and then it's going to raise up to some height. And they want to know how high above the water it goes. So you have the two parts. You have the acceleration through the water, and then you have the max height outside of the water. It's the two different motion problems. For the accelerating upward through the water part, you have to use the buoyant force. Just as a reminder of how to find that acceleration moving through the water, it's going to come from buoyant force up minus the weight down is equal to ma, where this m is the mass of the object, of course, right? What do we replace our buoyant force with? What do they tell us? What do they give on the formula sheet? Let me take a look. Oh, all they give you, yeah, mass of fluid times gravity. So buoyant force is mass of fluid times gravity. Remember that in almost every case is going to be replaced with density of the fluid, volume of the fluid times gravity, minus the weight, which is the mass of the object times gravity. And then I have the mass of the object times the acceleration. In this problem, I do not have the mass of the object, so I also need to replace the mass of the object with the density times a volume. So I have density of fluid, volume of the fluid, gravity, minus density of object, volume of object times gravity, equals density of object, volume of object times acceleration. Next up, I know that the volume of the fluid that is displaced is equal to the volume of the object because the object is completely submerged. So since we're completely submerged, these are the same volumes, and I can go ahead and cancel them out. Finally, I note the density of the object is 0.29, the density of the fluid. So the density of the object is 0.29, density of the fluid. And so I can go ahead and plug that in for these two density of the objects here. And then I'll have density of the fluid times gravity minus 0.29. Density of the fluid times gravity is equal to 0.29. Density of the fluid times the acceleration. Now I have the density of the fluid in each one of these terms, so now that will go away. And then combining my like terms on the left-hand side, I have 1g minus 0.29 g's, which will give me 0.71 g's, is equal to 0.29a. And then I can solve for a. Once I have the acceleration, then I just do a motion problem. So it's going to accelerate by that rate through the 0.79 meters to get to the surface of the pool. And then it's going to emerge with some velocity, which I need to find because that's my initial velocity for the max height problem outside the pool. It's a little bit of an involved problem. But if you don't spend a terribly long time on the buoyancy part of it, then it just quickly just turn into a motion problem. Oh, I'm looking at the solution and they mention work energy theorem. Oh, I see. They've plugged in density of water as 1,000, so that's why they have the two different densities there. The buoyant force. and the gravitational force, that's the ratio between them. So the work that would be done, that's right. So any max height problem, as long as it's a one-dimensional max height problem, can be done with work. And that's just essentially what they're doing here. So the motion inside the water, they're writing is that initial 1000 times v times g times 0.79. And then the work done by gravity is the opposite of that. So you have to do the 0.79 of gravitational potential energy that's gained, and then plus the height that you reach. So that's just a different way of doing the motion specifically. All right, question number 6 also is a homework problem. It is the tank problem, where you have a tank and you drill a hole in the side of the tank. A tank has a height, big H, and the hole is drilled a distance, little h, from the top. Excuse me, and this is the water level up here at the top of the tank. All right, how do we solve this problem? We relate the pressure at the top of the tank to the pressure at the hole. So pressure 1 plus rho g little h has to be equal to pressure 2 plus 1/2 rho v2 squared. Since the top of the tank is open, the pressure at the top of the tank and the pressure at the hole in the side are going to be the same. So those cancel out. Now I have density in both these. I can cancel that out. And I get that my V2 is equal to the square root of 2gh. Now that I have V2, I need to ultimately find the x distance that this stream of water strikes the ground. I need to find delta x. And I know delta x is going to be equal to velocity times time. And that velocity is going to be v2 times time. So this is time root 2gh. Last thing I need to do is find the time, and that's going to come from the y side, where on the y side, I know that my initial velocity is 0. My acceleration is negative 9.8. What's the other one that I have? Oh, I know that my delta y is little h minus big H, because it needs to be negative. That's why I'm doing little h minus big H. And then I can solve for time using delta y, the initial t plus a half at squared, old reliable. And this is little h minus big H is equal to negative 4.9 t squared. And then they give you big H and little h, so you can solve for t, plug it in here, and that'll give you your delta x. All right. Problem number 7 is just like a problem that we just did, right? We have a mass, we have an amplitude, we have maximum acceleration, unknown phase constant I don't care about, and they want to know the maximum speed. That's just like the very first problem I think that we did. We have a list of simple harmonic motion equations. Your x max is the amplitude. Your v max is the amplitude times omega. Your a max, your acceleration maximum, is amplitude times omega squared. Using those 3 relationships here, you can solve this problem in a few steps. Just make sure you convert to base units. Question 8 was a homework problem that we did not get this semester. So I'm going to say that it's less likely to be on the exam, but that doesn't necessarily mean it won't. I also need to mention that I have not looked at the exam. So when I'm suggesting what could or could not be on the exam, that's not coming from some special knowledge. It's just from doing exam prep for this class for 10 years. Yeah, all right. So I'm going to, the solution isn't even, it's literally just referencing the homework problem. With this problem, I guess I'll just mention, you have a car, the car has a mass, the 4 people have another mass, you add all those masses together. You're going over a road with corrugation 3.4 meters apart. That gives you your wavelength, and you can use that to find your your frequency with the speed, v equals m to f, and then you can relate that to the kx. This is a 2D wave, a y of xt wave, wave in motion problem. All right, question number 9. Traveling waves on a string, we decrease the tension by a factor of 2. By what factor does the wave speed change? How does wave speed relate to tension? V equals square root of tau over mu. I'm going to decrease the tension by a factor of 2. What does that mean? It means that my new tension, call it tension final, whatever, is just tension initial over 2. So if I replace the tension with tension over 2, I'm just introducing a 1/2, right? I'm just introducing a 1/2 underneath that radical. So I'm just replacing this V with 1 over square root of 2 times the square root of tau over mu. Just a question of that ratio. The ratio is 1 over square root of 2, which is equal to 0.71. We have two traveling waves, same amplitude, wavelength, and period, a phase difference of 80 degrees. What is a phase difference of 80 degrees? That's going to be, that's your phi. Remember that your phi value, it needs to be in radians. So 80 degrees, you do 80 over 360 times 2 pi. And that would be your phase difference. And what you do is you plug that in. This is actually a delta phase difference. What you do is you plug that in for one wave. And then if we need to find the amplitude, this would come from, yeah, this is going to come from, where did it go? The superposition of waves. This is what that equation is, alpha and beta. Alpha is 0, beta is 80 over 360 times 2 pi. And so you have 2 times cosine of this angle over 2. So that's just what the answer is. Yeah, so the amplitude is just 2 cosine phi over 2. As long as you know the phase difference, you can find the resulting amplitude. And this is just a simplification, again, of that sine of alpha plus sine of beta, where beta equals 1. All right. Okay. Question number 11. Yeah, okay, sound wave of a given form, kx minus omega t plus phi. Inside of it, that is your just fundamental definition for the sound wave. It's traveling through air with a speed, long horizontal tube, air molecule at A, uh, air molecule A at x equals 2.02 is at its maximum positive displacement. If I have my maximum positive displacement, what else do I know there? That means, first of all, that value is my maximum. That is my amplitude. That's what goes out in front. That's your S sub m, which is your amplitude for a sound wave. We also know that the velocity at that point is 0. All right. Air molecule B at 2.22 is at a positive displacement of 4 nanometers. So that's just giving me an x value and a corresponding S of x value. All molecules between are between. And we're asked to find the frequency of the wave. Okay. So this is actually a pretty good problem. We know that the particle at 2.02 is at the maximum of 6.2, which is also the amplitude. So we know that S sub m, and we know that, okay, we know that S is equal to S sub m cosine of kx minus omega t plus phi. Without sort of losing anything here, we can obviously ignore phi, and we can kind of just ignore both phi and t. And what we just need to see here is that, well, I guess we don't need to, we should keep omega in it. Just 1 second, let me think about this for just a second. V is omega k, right? Okay. Yeah, so we're going to use this to find k. So the first particle is that x equals 2.02, and we know that particle is at the maximum. So 6.2 millimeters, nanometers, so 6.2 times 10 to the negative ninth is the position, and that's equal to the maximum, which is the same thing, 6.2 times 10 to the negative ninth, that'll cancel out, times the cosine of kx. K times, what is my x? 2.02. All right, this stuff cancels, and you just get that cosine of k times 2.02 is equal to 1. Not entirely instructive. The second equation comes from a different k position. At that position, we have 4 times 10 to the ninth, 10 to the negative ninth. So this is my 4 nanometer displacement is equal to 6.2 times 10 to the negative ninth times the cosine of k times this location is given as 2.22. All right, and yeah, so we can simplify a little bit here. You end up with 4 on 6.2 is equal to cosine of k times 2.22. And ultimately, we need to also consider the other stuff that is included inside. That is something we could ignore for a second there, but the minus omega t plus phi. And this comes from this first equation. In this first equation, we have k sine of kx, and we have that minus omega t plus phi, and that's all equal to 1 from this equation, because we canceled out these two terms. Since this is all equal to 1, that means that my stuff inside of it has to be equal to 0, which means that this stuff is equal to this stuff. It's a little bit of hand wavy, but the point is that we have, again, all of this inside, and I have cosine of all of this is equal to 1, so long as x equal to 2.02. That means that this right here has to be the opposite of this stuff in order to give us 0. That gives us cosine is 1. So included inside of this cosine function here, we also have that minus omega t plus phi, and we also again know that it's just equal to the opposite of this. So we should put in there a minus k times 2.02. And by substituting that for the minus omega t plus phi in this equation, we take care of that, and then we can go ahead and combine our like terms. We end up with 4 on 6.2 on the left-hand side is equal to cosine of k, 2.22k minus 2.02k is going to give me 0.2k. And then I take the inverse cosine and solve for k. What that's going to give me is the wave number. And I know that the wave number is 2 pi over lambda. Ultimately, though, I don't need lambda, I need the frequency. And that frequency will come from k, quite a few equations here. The frequency, so once you find k, I know that my speed is equal to omega over k. And then finally, since I want the frequency in hertz after I find omega here, with the velocity, because it's a sound wave, your velocity is 340. Well, they don't even give you that. Oh no, 344. They do give you 344. So once you find your omega, then you can go ahead and plug it in and say that omega is 2 pi f. Man, this problem sucks. Moral of the story, if you see this problem in the exam, skip it. Save it for last. For a sound wave problem specifically, especially because you have not done a whole lot. Very quickly covered at the end of the semester. All right. A well with vertical sides, water at the bottom, resonates at a given frequency, and at no lower frequency, the air-filled portion of the well acts as a tube with one closed end and one open end. One closed end and one open end. Where did I see that? This was many, many pages ago. One end closed on one end is that frequency equation where we have a standing wave. Good. So we get a chance to experience a different version of the standing waves. This is going to be the one where you're open on one end. When that happens, here's my tube. I guess it's a well, so I'm going to draw it kind of on its side. Here's the bottom of the well where the water is, and this is the top where you don't want to fall in. And the standing wave is going to have a shape like this. If it's in its fundamental harmonic, at your closed end, you have a node. At your open end, you have one of those antinodes. I don't know if I said that word yet, but there's an antinode, your maximum vibration point. Great. So how much of a wave do we have here? We just have just 1/4 of a wave. So this right here, this length is equal to 1/4 of a wavelength. And what do they give us? They give me frequency. And since they say we're at no lower frequency, that's how I know that I'm in this. This is the fundamental. This is n equals 1 on that closed on one end equation. So we also could use that. Frequency is n equals 1. So it's nv over 4L. So I'll just be v over 4L. It's the same sort of thing here. They give me the frequency. They give me the density of the air and the bulk modulus. Density and bulk modulus, where did that come from? We've only have one equation which has bulk modulus. It's V is equal to the square root of the bulk modulus over the density. So density and bulk modulus given in the problem, plug it in for V, plug that in here. What will the length be of the well? They say how far down the well is the water surface. We are given a frequency, so we plug that in here. Great. And then you get out the length, and the length here is 9.87 meters. Okay, one more problem, and then I am I'm going to drink some water first. One more problem, and I will have at least taken a shot at all of the new material in the last few semesters. And the last problem is going to be a Doppler effect problem. All right, we have a French submarine. Here's how I know. A French submarine and a U.S. submarine are moving toward each other. Immediately, I know it's a Doppler effect problem because submarines use sonar, which is sound waves, and they bounce off of things and read the sonar. Another thing that if it shows up, it's absolutely about to be a Doppler effect problem, a bat, because bats use sonar. That's why they scream at things they can't see, but they scream, and then their ears can do the Doppler effect for them. They like learn how to do that automatically. All right, it's called echolocation. French submarine, US submarine move toward each other. Great. The French sub moves at one speed, US sub moves at another. Who is our source? Who is our observer? We don't know yet. The French sub sends out a signal, and we want to know what frequency the US sub detects. All right, so what was my rule? My rule is source on the left, observer on the right. So here's my source, here's my observer. For this problem, which one is the source? The source is the French sub releasing a 10 or 50 hertz signal. So this is the French, and this one is the US sub. They are moving toward each other. So here's the direction for the velocities. The French sub will have a negative, in the US will have a positive. And the French sub is moving at 60 kilometers per hour. And since it's to the left, that's going to be negative. And very annoying that it's in kilometers per hour, because I do not want to do that conversion. Oh, kilometers per hour to meters per second it's 16 over 36, right? 8 over 18, 4 over 9. 4 over 9? Multiply 60 by 4 over 9. I think that's right. Anyway, negative 60 kilometers per hour. You'll have to convert that. But I think you multiply by. Anyway, the US sub is moving 70 kilometers per hour to the right. So that'll be a positive 70 kilometers per hour. And the French sub sends out a given frequency. We're given the speed of the sonar waves. That'll be the V for the V of sound in the Doppler effect. So this French frequency is 1050. and I ultimately need to find the frequency observed by the US. All right, here's the equation again as it looks on the formula sheet, but I'm actually going to abbreviate a little bit. Frequency observed is equal to the frequency of the source times V of sound plus or minus the velocity of the observer over V of sound plus or minus the velocity of the source. And my frequency for my source is 1050. The V of sound is given the problem 5470 kilometers per hour also. Oh, great. Kilometers per hour will cancel out of everything. I know I always say convert all of your units to base units before you do any calculations. I agree with that here. However, I don't feel like doing it. And I know that the units are going to cancel. So do as I say, not as I do. The speed of sound is 5470. The velocity of the observer is the US is my observer because it's on the left side here, positive 70 over 54, 5470 again, and then plus or minus the velocity of the source. Velocity of my source is negative 60, so it's a French sub, minus 60. And calculate all this stuff, and you'll get out 1075 hertz. Okay, so so we input 1050 because of the Doppler effect, because they're coming toward each other, we should get a shift up. The sound should be higher than it actually is. In fact, it is 1075. Great, I am kind of out of fumes here. So that was, I think, a decent review of at least two exams worth of, two finals worth of new material. And yeah, great, I'm gonna go ahead and put this up. And good luck, everybody, on your final exam. It's been real. Everybody have a good break and everything. And cool. All right. Goodbye.